Greetings all. Till now we were looking about the lumped heat capacity method for the unsteady state heat transfer, and by the end of this lecture you will be able to explain the thermal time constant pertaining to the unsteady heat transfer, and we have seen the what is the definition of this thermal time constant so in the last class. So just to recapitulate, it is nothing but the product of the convective heat resistance, convective heat resistance and the thermal capacity of the medium or solid. All right, so convective heat resistance we can write as 1 by h times surface area of the body times the thermal capacity, which is nothing but the mass of the body, times specific heat, which is nothing but represent the ability of the body to store thermal energy, right? So this is the representative relationship of thermal time constant with respect to the heat transfer coefficient and geometrical and thermal properties of the body. All right, so by seeing this relation we can have so many inferences. So if we write m as rho times volume of the body, okay, and c as it is, and in the denominator h times as, then volume by surface area we all know it is the characteristic length. So we can see that rho c times lc, we can write like this: volume by surface area is lc, which is nothing but the characteristic length of the body, and the denominator h as it is. All right, so I have told you in the previous class also that tau star represents the thermal response of the body. For faster response the time should be less, right? So we can have faster thermal response of the body if we have the body which have very low specific heat. Low means low ability of the medium to store thermal energy, and low density means material is lighter and it is placed in the medium which is having very high heat transfer coefficient. All right, and also characteristic length should be small, means the dimension which is characterizing the body should be small, means the body should be small in size as compared to the other dimensions of interest for the heat transfer, right? So let's look at some numbers and inference and create some more details about this thermal time constant. All right, suppose we have this thermocouple placed inside the pipe, and we want to measure the temperature of the flowing fluid inside the pipe. All right, so hot fluid, let's say hot fluid is flowing inside the pipe. Initially the thermocouple temperature, let's say it is T0, and we are saying that this thermocouple has T0 temperature initially. All right, it is at steady state. Okay, so when the fluid interact with this thermocouple, its temperature will rise. All right, so its temperature will rise, continue to rise, and after some time it will reach asymptotically to the outside fluid temperature, which is nothing but T infinite here. All right, so on the x-axis represents time and on the y-axis temperature. All right, so what we are seeing that we are interested in at after how much time we can approximate that the thermocouple has reached the ambient fluid temperature. All right, so to characterize or to find this time, to find that time, thermal time constant will help us. All right, so let's do, so before doing calculations, let's look at one more aspect. Suppose we have two thermocouples, one is behaving like the red one and one is behaving like this one, the green one. So let's say green one is thermocouple 1 and red one is thermocouple 2. So according to you, which thermocouple is good? Of course, yes, green one. Why? Green one, right? Why? Because it is taking less time to reach the ambient fluid temperature as compared to the second one. Okay, it means it has fast thermal response, or in other words, it has low thermal time constant. All right, so this was this what I want to say about this. So let's now do some calculations about finding this, means how this we can find this value, that after how much time we can say that the thermocouple or any lumped body have reached the ambient fluid temperature when we are measuring the ambient fluid temperature. All right, we are doing the lumped heat capacity or lumped analysis. All right, we have seen that for lumped body this relation is valid, right? We have derived this relation. So if we put T as tau star, then we will see by calculation that T minus T infinity will be 0.367 times T naught minus T infinity. Means this is the temperature difference, T naught minus T infinity, and at T is equal to tau star. So let me draw this on the other way. So if it is, this is T infinity and this is T naught initial fluid temperature, and this is the thermocouple response, right? So at T is equal to tau star, let's say T is equal to tau star, the temperature T minus T infinity is 0.367 times of the initial temperature difference. All right, so if we go further at T is equal to 2 times star, then T minus T infinity, that difference will reduce further. All right, so it will come out to be 0.13 times T naught minus T infinity. So it will move further up. The difference will reduce if we go further in time. So similarly for T is equal to 3 times tau star, we will get 0.05 times. Okay, how we are getting it? Because it is 3 tau star by tau star, means e power minus 3. This is e power minus 2, this value. All right. So in practice, we say that thermocouple or any other body lumped, which is assuming it to be lumped, has reached the ambient fluid temperature if time is greater than or equal to 4 times the thermal time constant. All right. So for this, the value is 0.02 approximately. So it means t minus t infinity is approximately 0.02 times t naught minus t infinity. So if this is, so it means after this tau star, 4 times tau star, the difference between the thermocouple temperature and the ambient fluid temperature is very negligible. All right. So that is how we can use the thermocouple time constant in the unsteady heat transfer analysis, and its application is used in the thermostats, which is used to allow the flow of coolant around the engine